application. I don't know why you would do this, but if you were scaling it down, right? In this region, what you would hear is all of your sound, right, would kind of like get out of phase. So like the higher stuff would get like a little like left a little behind, whereas the low stuff would stay in tune. So your audio signal would just sound weird. And what I'm going to do, hopefully on Wednesday, is I'm going to like try, if I can get sound figured out, I want to show you like kind of like what these distortions can sound like. But yeah, so that's what the phase plot gives you. We'll talk about this a lot more. Okay, so I just want to kind of like finish like kind of high level on this. So almost always, right, our signal is going to consist of a bunch of different frequencies. We're not just going to have like one frequency. You're going to have like my voice, right? There's some filtering going on here with this thing. And so what we want to do is kind of think about it as like, there's a bunch of different frequencies all happening at once. And as you know, right, based on the example we did with two sources, you could still kind of apply the same basic idea of impedances and frequency response and so forth. You have many frequencies at once. You just do superposition. So for example, like if you push a 1 on a phone, you get a sound which is really just two signs added together. Antennas, as I mentioned, they should theoretically pick up all frequencies of all transmissions in the universe. And what's kind of neat is, and this is really EE20 stuff, but we're going to talk about it a little, is that if you're given a signal in time, you can convert it into like a frequency domain representation. So what I mean by that is there's a math technique where you can take something like here I have sine 3000t, and I could do something to it, some kind of math thing where I'll end up with a plot here that says I have a frequency of 3000 and very little of anything else, right? And if that was a perfect sine wave, there should be an impulse function at that. So this is beyond our class, how to actually do this. But I think conceptually it's really useful to think about how filters work, right? Like a 3000 hertz thing, there's only one thing happening if you'd like. Like if you wanted to do a phasor problem, you would just need one source to peg what it does. For example, though, you might have like, here's in time, right? Even just having two signs at one time look kind of ugly, right? This is this is when you push 1 on a phone. If you were to go and look at it on the scope in the lab, over time it would look like that. If you Fourier transformed it, you'd get 2 peaks, one at each of the actual frequencies, like behind the scenes there, which are 697 and 1209. So what's cool about filtering, right, is if we take a filter, for example, this one right here, and the cutoff frequency is around 1,000, and it's really steep, right? So as soon as I go like a little over, we're dropping like 10 orders of magnitude. What we'll see here, and actually it's 7, right? So it's a 7th order filter because you're dropping off the power of 7 of the frequency. But right here, right, if you take that filter on the left, you have a circuit that does that, and you apply these two sources, like a phasor problem like you've been doing, and you plug them in and you use them as the two sources, what you'll find is that this one right here will just get like annihilated and made very small, whereas this one will stay. And so this is like a really fundamental and very cool idea in like 30 seconds, and we'll talk about it a lot more, but this is kind of like why filtering is neat. Yeah. Okay, so I'll just mention for Wednesday, just to draw the distinction so you've heard of it. So there's passive filters, the one we did in class, right, with the resistor. Like the ones we've been talking about so far, they're just resistors, capacitors, and inductors. So they're passive. They don't have any sources. They're nice because they don't need any power, and they can handle big voltages because there's nothing to worry about saturating, and they're cheap. The other kind of filter, which you'll build on Wednesday, is an active filter, which is basically just the same kind of thing, but with op amp. So you'll have plenty of those in your homework. And the thing about active filters is that you can get more complex answers, so the homework will be harder. But they're really nice, right? So the other nice thing about them is they give you this independence of load. Okay, so that's active filtering and passive filtering. I'll be in 240 in a little while. If anybody wants to talk homework, Okay. So let's do one more thing on this example here. So what we were just saying before is we did this calculation and we found that I of t is equal to this function, right? So let's look at its various properties because we went through and did all this work to find it. So what do we get? So what you find is that the current has the same basic shape as the voltage. It is a cosine. That is good. If you go through and do it a long way, and do the proofs, that's the case. But yeah, you should always get a cosine like that, or a cosine with some offset. What we find is that the current is a lot smaller though than the voltage. So this is not to scale, of course, otherwise you wouldn't be able to see this. But you get a much smaller current. And we also see that the current leads the voltage. So in other words, he hits his bottom of his period, and then this guy hits next. And the time between those two is just given by pi over 4 radians. Since it's pi over 4 radians and omega is 100, right, the time it takes to actually move through that much, to move pi over 4 radians is pi over 400 seconds, right? So that's what our voltage and current relationship looks like. So in that sense, whenever you put a pure cosine in, the answer isn't all that exciting, right? You end up just getting a pure-ish cosine out. So also, Luke brought up a good point, which is that here this is in steady state, right? So if you have, so that's sort of like once you activate this cosine, there's going to be a slight delay where there's going to be some distortion as the circuit kind of ramps up to being this shape, right? So typically what you'll get in this case is you would have kind of maybe the first half period or 2 periods or whatever will be a little smaller than they should be. And it's an issue, but hopefully you've designed your circuit so the homogeneous response doesn't last very long. Okay. So what else? Let's see. All right, yeah. Well, I guess I'll do a harder one. I'll at least set it up, but you guys can tell me if it's worth actually going through and finishing. Okay. I'll also mention, so as you guys saw in homework 5, it was non-debugged at first, but I went through and did the solutions, and nothing was broken except for the fact that one of the answers in the back of the book had an error. So, but everything else should work fine, and I gave you the rough approximate answer. Because one of the phasor, or one of the complex number exercises, the number in the back of the book is wrong, and I tried figuring out what was up, but yeah, it's 4D. You'll see what I mean. Okay. So let's say we had a bigger circuit. Okay, suppose we wanted to go through and solve this thing. And what are we trying to find? Let's say we're trying to find VL of t. Okay? So if we wanted to find VL of t, what would we do?